So, with everything we've learned now in terms with steric geometry, shape, and bond angles, we can make a table with basically all the information we have. How this works is we have number of electron groups. Okay, this is what we're referring to as the steric number. Okay, so this is essentially steric number in this column. And then we have bonding groups and lone pairs. Okay, so you're going to have, for steric number 2, you're going to have linear, right? Steric number 3, you're going to have trigonal planar, but you can have trigonal planar or bent with one lone pair and walking down the line, right? And so also for 5 and 6, different number of lone pairs. Again, 5 is based on the trigonal and bipyramid, and 6 is based on the octahedral shape. Now, this looks like a lot of information, and it is indeed a lot of information. As I said too in the first video in this chapter, you really have to work to visualize this well. If you can visualize this well, this will be easy for you to memorize, and there'll be actually very little memorization. You can kind of just think about it. If you're rote memorizing this, well, maybe some of you can do that, and I'm sure all of you can do it, but it's just harder, and not really what I want you to do. So please try your best. Either get a model, again, make a model with toothpicks and candy or marshmallows or something, or go on those links that I shared. There's a lot of resources on the web campus for this chapter that you can look at for visualizing molecules, okay? Again, remember that you have bond angles, real bond angles that are oftentimes less than the ideal bond angle. For water, it's steric number 4. It doesn't have a bond angle of 109.5. It has a bond angle of 104.5 because the lone pairs are repelling. So remember that lone pairs take up more space in this theory and they repel, causing the bond angle to contract from its ideal value. So we're going to go into a little bit about polarity of molecules now. And so just to remind you from our last chapter, this had to do with differences in electronegativity. And so if we had 2 fluorines, even though those are both highly electronegative elements, fluorine is the most electronegative element there is. The tug of war here between these 2 bonds is equal. And so it's kind of like each fluorine effectively is getting 1 electron in this 2-electron bond. But if you have a hydrogen fluoride molecule, right, things are very different. And the fluorine is winning the tug of war because it's way more electronegative than hydrogen. And so it's not quite an ionic bond. That would be an extreme version of unequal sharing where you actually have electron transfer. But you definitely have a dipole where you have slight negative charge on the fluorine and a slight positive charge on the hydrogen. Again, it's not cation and anion because it's not an ionic bond, but it's close. Okay, it's sort of in between non-polar covalent and ionic. We call it polar covalent. We can come up with these electron maps, remember, and we draw it with an arrow going towards the negative charge, the charge of where the higher electron density is. And we can calculate this with just looking at differences in the Pauling electronegativity values. Okay, when we calculate those values, that can tell us whether or not we have relatively equal sharing, called a covalent bond. That's going to be less than or equal to electronegativity difference of 0.4. In between 0.4 all the way up to 2, we're going to call polar covalent bond. Higher than 2 difference electronegativity, at that point, you're going to have a metal and a non-metal in most cases, and that's going to be considered an ionic compound where you have such a strong tug of war that you have electron transfer. So polar bonds don't equal polar molecules, and I alluded to this earlier last chapter, but now we're really going to dive into this because we can know the shape of molecules. Okay, and so think about if you have little bar magnets, right? If you have 2 bar magnets this way, you're going to have repulsion between the south and the south. But if you have 2 bar magnets this way, you're going to have attraction. And so you have to add up kind of what's happening between the 2 different bar magnets to figure out net, is there any effect, right? Is there any movement to the left or any movement to the right? And that's going to be based on the shape. So a polar molecule is going to typically have polar bonds in it, but polar bonds don't necessarily mean a polar molecule. That's what this title is telling you, because the individual polar bonds could cancel each other out to give net no dipole. Okay. And so here are two examples. Look at carbon dioxide. You have a polar bond in carbon and oxygen. Oxygen is more electronegative than carbon. So you have electron density pulling you to the left. But then you also have this oxygen pulling you to the right. And we know this is steric number 2. This is molecular shape is linear. And so you basically have a tug of war equally going on to the left as the right. Overall, you have nothing. Contrast that with water. Water has a steric number 4. That ends up giving you a bent geometry, right? And so now this is bent, and oxygen is more electronegative than hydrogen. You're going to have a polar bond going this way towards the oxygen and a polar bond going this way towards the oxygen. Those are going to add up, giving you net polarity pointing towards the oxygen going straight up, how I've drawn it, okay? So that's how the dipoles can either cancel out or add up to give you a polar molecule.